Welcome to another exciting image processing class. Today I thought what I would do is give you a little lecture on color, and then I would columnate. Anyway, I'd end up with the lecture assigning a midterm. So I'm thinking there should be a midterm, and it should be due in 2 weeks. And in 2 weeks, it'll be just before the spring break. And as a result, there won't be anything due over the spring break. Did you cut your mustache? Oh, wow. You look much younger. So let's see what we can do about that. Was there like a reading assignment due today? And what was the reading assignment? I forget now. We're going to read this book, right? Convolution. So we have finished the reading with convolution, and you guys probably finished up with chapter 8. The next one is on there's a bunch of chapters 9, 10, 11, and 12, which have to do with spatial filtering and applications of convolution, which I think are very interesting. But what we're going to do is we're going to get back to those later, and what I'd like to do now is look at this basic idea of color. And so, what I'm going to do... Beg your pardon? Where is everybody? I don't know. They're out having a good time. What I'd like to do is see if we can understand a little bit more about what color is. And in order to understand color, we want to understand the electromagnetic radiation that we can see, which we refer to as light. Light in the color band that we can see varies in wavelength from 400 nanometers out to 800 nanometers. If we go at higher frequencies than 400 nanometers, the wavelengths get shorter, and we call it ultraviolet. If we go at wavelengths that are longer than 800 nanometers, the wavelengths are called infrared. So when we look at the, I'll call it big spectra, right? The big spectra, and then we look at what we can see. What we can see is really little compared with the big spectra. When we think about ultraviolet, some of the higher frequency stuff, which is over in here, we start to think about stuff that tends to get into the area of what's known as ionizing radiation. Ionizing radiation is very important for us. As we get into ionizing radiation, what happens is the photons have so much energy that they can knock the electrons out of the orbit of the atoms in our body. Once they start to knock the electrons out of orbit, our atoms become charged. Once our atoms become charged, that charge can cause alterations in our genetic makeup. Those genetic mutations, okay, we'll call them mutations. Those mutations can cause things like cancer, cooties, big-time serious nastiness. And so this is why people give you limits on how much radiation you can get in a given year. There is a very famous 2011 accident with a nuclear reactor in Japan in the prefect of Fukushima. Outside of Fukushima, there is a town that I just read about this morning. I'm going to mispronounce it. I think it's called Okima. And it's a town of about 11,500 people, evacuated rapidly. No one can go back there. because of the high level of radiation, which will only be cleaned up if people spend an amount which no one has even bothered to estimate yet. That's how expensive it will be. People who cannot go back, including the mayor, say they've been living there for 19 generations. People in Japan can live in one place for a long time. Now, yeah, I don't know, what 19 generations means in Japan. I imagine people are relatively long-lived. 19 generations could be 20, maybe 30 years per generation. We're talking about people who have been there for 400 to 600 years, and they can't go back because ionizing radiation, right? So this is the kind of stuff you're thinking about when you start to think about ionizing radiation. We're talking gamma rays. That's way up in here. So that's the stuff that's keeping, people away from their homes. When you start to think about ASML, ASML is a company that does optical lithography using soft X-rays. Soft X-rays are right in this wavelength, right about in here. So we're thinking perhaps 153 nanometers, certainly well beyond the ultraviolet. If you're thinking in terms of, what it is they have to do to make those X-ray sources, well, the answer is they take droplets of tin and they hit them with lasers, high-powered infrared lasers, and then they proceed to create a plasma, and then the plasma is what generates the high-power source. That's what Cymer does. Cymer, it was a separate company. ASML purchased them out because they had that unique ability to create these soft X-rays, which they needed for the next generation optical lithography. At the other end of the spectrum, you see the microwaves. Once you're thinking in terms of microwaves, think Bluetooth. That's about 2 gigahertz. Give you a frequency wavelength tutorial now. Most of the time, electromagnetic wavelength radiation travels at the speed of light. So speed of light, round numbers, 300 million meters per second. Right? That's round numbers. So then now if I have something that runs at 300 megahertz, right, I figure the wavelength is like distance equals rate times time. And when I look at the rate, I look at the speed of propagation of the energy in the media. When I think about the distance, I think wavelength. So now wavelength equals speed of propagation of the electromagnetic radiation in the media, and then I can multiply by time. So that's cycles per second. And so if I take 300 million meters per second, that's my I'll call it speed of propagation in the media, and divide through by, let's say, the wavelength. Perhaps it's 1 meter, right? At 300 megahertz. So if I take the millions and cancel them out, 300 million. I guess I should probably do this with the slide, right? That's the best way to do this. So let's do it with the slide, because I'm doing it in my head, and that's no good, and you guys may not be following me. So we'll just do this thing here. Wavelength to frequency. So distance equals rate times time, right? And the analog of that is wavelength, lambda, equals c, rate of propagation of the media, and I'll just divide it through by frequency, f, because that's cycles per second. And so then if I want to figure out the wavelength is 1 meter equals 300, I'll call it million meters per second. So perhaps 300 times 10 to the 6 meters per second. And then I'll divide it through by 300 megahertz. I guess it's Hz, like this. And so that comes out to be 1 meter. So rule of thumb, if you take the number in megahertz and divide it through into 300, you'll be able to get your wavelength, rule of thumb. So if I'm running at 3,000 megahertz, that's 3 gigahertz, I'm going to be running at 1/10 of a meter. 1/10 of a meter is like 10 centimeters, 2.54 centimeters in an inch, right? So you got to figure that's something on the order of 3 or so inches. So 3 inches and 3 gigahertz, thereabouts. So I'm just ballparking it for you. So when you're looking at these frequencies, sometimes the frequencies are hard to visualize or appreciate. So you can instantly start to convert these things into what I would call wavelengths. Right? So that's kind of where I'm at with this, and if you're thinking, 3 megahertz is a radio wave, which we would call, what do we call that? That's VHF, I guess. Certainly 100 megahertz is VHF. I'll call 300 megahertz, it's almost UHF, but it's in the VHF-UHF range. Then microwaves, now we're talking gigahertz. And so now we're getting into the tens or less than tens of centimeter range. And once you start to get into the millimeter range, you're getting closer to infrared. When you're in the nanometer range, you're getting close to visible light. So if nanometer is visible light, say 400 nanometer is visible light, where are the X-rays at? It will, beyond nanometer comes, I don't know, what do they call it, picometer? So now we're in the picometer range with X-rays, and that's the kind of wavelength we're at. Yes, sir.
So, all right. So we can see the visible spectrum, and I heard like animals can see other spectrums, right?
Yes, yes. Snakes can see in the infrared.
Do they actually see a color?
Well, they are able to sense it. The question of what exactly they are perceiving, we don't know. But they can it's not invisible to them, whereas it is invisible to us.
Is there a way that we can like see X-rays or radio waves or anything?
Absolutely, yeah. If you take a CCD camera and you point an infrared remote control at it, it could be in your iPad or your iPhone or whatever, you'll see it light up. Now the CCD camera will register it as a bright white light. Your eye will not see it at all. So it sees the radiation. The question of what color it translates to in the human visual system is open, because that's almost arbitrary. Once you start to perceive intensity at a wavelength that's not normally visible to your eyes, through some instrument, you can make it any color you like when you go to translate it to your human visual system. I'll give you an example. There are radar antennas orbiting the Earth, like Hubble, the Space Telescope, which are sensitive to X-ray. There's the Chandra telescope. That's all it sees is X-rays. So if you're thinking about what it is you want to do to represent X-rays to the human visual system, the answer is whatever looks right, whatever seems appealing visually, because you're using scientific visualization on a measurement that you can't normally perceive. Right? So if I said to you, well, over here in my infrared, camera, I can see the heat coming off this window, and you say, oh, well, how shall we visualize it? I could say, well, maybe it should be different shades of red. right? And where it looks really hot, it gets really red, and where it's cold, it'll make it blue or something. So you can say to me, is it really that color? And the answer is no, it isn't. It's just a different temperature. So then you say, well, why did you make it that color? I say, well, because I think blue means cold and red means hot. I don't have a good answer for you. So it's just the way I'd like to visualize it.
That's interesting. I was always thinking about that.
So if the X-rays are 10 to the 18, and we're thinking millions are 10 to the 6, then we're looking at something that's... Oh, thank you. We're looking at something that's 10 to the 12th smaller than a nanometer, so 12 orders of magnitude smaller, right, than some of these things that we've been thinking about, than radio waves. So if nanometers, right, 10 to the 12th, and this one is 6 times smaller. What's a million times smaller than a nanometer?
Is it a micron?
No, microns are thousands. Nanometers, after nanometer comes pico, that's 6. Something smaller than, probably femtometer. Something like that. Something really tiny. So this is the relationship that I'm using. And I like to think about energy propagation as something that has a speed. And the speed limit for energy propagation is a function of the kind of energy you're dealing with. So sometimes it's electromagnetic energy, sometimes it's sound energy, sometimes it's energy in a specific kind of medium. So for example, if I'm dealing with energy going through a piece of crown glass, it may slow down quite a bit. So light, the speed of light in crown glass changes. So it's an interesting point. The speed of light is not a constant. And in fact, as the light changes, it bends, and that's a function of refraction, right? Basic electromagnetic property. So when we think about the energy in the photons, we start to think in terms of frequency and Planck's constant. That's a typical way in which we talk about energy in a photon. And the higher frequency stuff has more energy. And in theory, when we start to look at RGB images, the RGB images can be represented by different wavelengths. So a lot of times what happens when we look at, I'll call them direct color images, is we're looking at 24-bit or more pixels, that is pixels with 24 bits of dynamic range or more. That's usually meaning that there's 8 bits of dynamic range for red, 8 bits of dynamic range for green, and 8 bits of dynamic range for blue. And typically, when you think about these things, you think, well, gee, there's a wavelength that corresponds to the apparent color. And it's possible to convert from an RGB color into a wavelength, because each wavelength has a different apparent color. And the reason why that occurs is because our eyes have, I'll call them color filters. And these color filters are going to have peak spectral densities around red, green, and blue. And we have the greatest response in the green area, which is right around 532 nanometers. But there's a smooth transition as you change wavelength in terms of what color it is appearing to be. There are perhaps 15,000 color names in the National Bureau of Standards. I don't know them all. I couldn't know them all. But there are other ways in which we can use what I call the Crayola crayon concept of color, which I think we all share. we know the 8 basic colors in the Crayola crayons, right? I know white, black, I think there's blue, red, yellow, orange. Perhaps there's a green, and maybe there's a gray. I think that's probably all the Crayola crayons I know. Now, with those Crayola crayon colors, I can make shades, right? Greenish blue or yellowish red. And by using those color names, I can convey color ideas to you in an efficient way. Whereas if I said chartreuse, I think you and me are both clueless because we don't know what that looks like. And I should, but I don't. And so this is one of those things where when we start to talk about color, sometimes it's more efficient for us to talk about it in terms of wavelength, especially if we're trying to be scientists that are trying to measure electromagnetic frequency content. And so, in fact, what we could do is we could say, I have a laser, and it's emitting 532 nanometers. And you could say, aha, you have a green laser. Now, I could have just said, I have a green laser. But maybe it's better for me to tell you it's a 532 nanometer laser because there could be another laser that's 556 nanometers. Now, it's also a green laser, but it's not quite the same color green. Right? And if I told you I had a 640 nanometer, I don't know, teeny weeny heeny, right? The little helium neon laser, that's not going to be exactly the same frequency as a direct injection laser diode red laser pointer. It'll be a different color. But they'll both be red. So specifying it by color makes good sense. So when I think about saying, hey, I got a red laser, what does that mean? And that means that you look at the laser output and you see what you call red. You give it a color name because that's how you perceive it. So when you talk about color, you're really talking about perception. But if you talk about wavelength, you're talking about an absolute measurement of power spectral density. So that's quite a different thing. So if I say, aha, it's a 532 nanometer laser, and you say, it's a green laser, you're equating it to what you see, and I'm talking to you about it as though I were a physicist making a measurement, which is, two different things that are roughly equivalent. So when I start to think about how we see color, I think about our brains and how they process what our eyes are sensing. And so it's a question of sensation and perception, because there is no color without perception, and there's certainly no color without sensation. And so when I think about image processing of images that we see, I often think about what the observer perceives. Therein lies what I would call some of the basic fundamental questions that deal with the eye-brain interface and what the mind does to process what the brain perceives through the eyes. And so this gives us what I will call biologically motivated image processing. A lot of times what happens is somebody comes up with a sensor, new way to do imaging. In my case, it was an MRI. And they didn't know that all of my image processing subroutines use 8 bits per pixel. They didn't care. So they said, we're going to do what we want to do with as much dynamic range as we can muster. So instead of getting 8 bits per pixel, they created a DICOM image in medical imaging format, which gave them more dynamic range. 16 bits per pixel. Hubble Space Telescopes give you even more than that. So then, what are we supposed to do to take a 16-bit per pixel image and convert it into a 8 bit per pixel image? That's a big question. That's an important question, because if we distort the image in a way that's irreversible and we lose a lot of detail, then all of a sudden we've reduced the usefulness of the instrument that does the measurement. That's kind of important. In fact, it's so important, I'm making it your midterm. So it would be really good for us to learn more about how color works and how we perceive it, and then how we can, I'll call it, re-quantize color. Re-quantizing color means taking high dynamic range color and making a lower dynamic range color.
Is that what you did?
Well, that's what we will do for our midterm. So this business of re-quantizing an image by virtue of reducing the number of colors available is, I think, a very topical thing. When people start to talk about measurement of light, they talk about the power spectral density of the light. That is to say, what are the frequencies contained in the light? Now, here's an interesting experiment that I ran recently. If you take a 400 nanometer direct injection laser diode harvested from a PlayStation, which I'm liking to take apart, and then you do the same thing for a red laser diode and a green, you can take the laser diodes and you can converge them onto a single point and make a nice white light. But that white appearing light really consists of three quite distinct and very narrow band laser diode emissions. And by narrow band, what I mean is if you look at the 403 nanometer output of a Blu-ray laser, it's plus or minus 2 nanometers. And it's not going to be plus or minus 2 nanometers in a broadband way. It'll just be moving up and down about 2 nanometers as a function of temperature. So it'll always be very close to one specific frequency. And you will be able to clearly separate out those dots if you take a diffraction grating, because the diffraction grating will change the angle at which the light propagates as a function of its frequency. So any diffraction grating that you put in front of that white illuminating dot will clearly separate into 3 different dots with 3 different pure colors, really pure colors. So you can I'll call it analyze the power spectral density of the light using a grating. The grating is the analyzer, if you like. So it's almost the equivalent of a Fourier transform, giving you power spectral density. So photons are interesting things, right? They get emitted, they get reflected, and they get absorbed, right? When they are reflected off of a target, in general, your eye will see them through absorption. And when they're absorbed, they tend to give us some sort of alternative energy form. For example, after they hit our eyes, they create an electrical signal which travels to our brain. So when we think about these different colors with color names and the different frequencies that they arrive at, it's pretty easy for us to get our I'll call it Crayola-crayon concept of color identified by wavelength. Violet, that was the Crayola crayon I forgot. See, I can only remember 8 color names. Red, orange, yellow, green, blue, violet. I think they have a white color crayon and a black one, and that's it. Of course, you can get the box of 64, but they come with color names I can't remember. I can barely remember the 8. I think people who are skilled in the field of art probably know the color names. They have all the Pantone names and such. So when I think about lighting, I think about material properties that cause the appearance to change. And there are a few different things that you can do to change the appearance of something. For example, this is a glossy cover. This is what they call cover stock, right? So they give you a nice shiny gloss. That glossiness comes about because it has a coefficient of specular reflection, and it gives us a shininess that you can see. And if it were metal, then it would have an even higher coefficient of specular reflection. If we look at, for example, the 60-pound cover stock that they used for the tip-in on the book, you can see it's very shiny. Whereas if you look at the paper, it looks very dull in comparison. And that shiny paper is there because it reduces what's known as the dot gain. Dot gain occurs when you apply ink to a page and the ink gets absorbed. The ink will tend to spread out. But if you use shiny, glossy stuff, the ink doesn't spread out as much. Consider if you look at a copy of newspaper with color images on it, like USA Today. The color images look all blurry because of dot gain. Newspaper has very high dot gain. When you look at something like Cosmopolitan or quality printing like that came out from this book on 60-pound gloss, you can get 155 lines per inch of color. But if you try to do that on newspaper, your best bet would be to crank it down to perhaps half that. 83 lines per inch is typical for USA Today. So the dot gain is critical when you're trying to reproduce color because the rosettes which they use are red, green, and blue-ish type colors. Actually, they're in a subtractive color synthesis system known as cyan, yellow, and magenta, and black instead of red, green, and blue. Why? Why would they use different color primaries when printing than we would use, let's say, when projecting light from a video projector? No, it's not because it looks better. Color primaries are different for a fundamental intrinsic reason. Yeah. Okay, why do they use different color primaries when printing than they do when, let's say, displaying on a color monitor or a video projector? Yes, it's RGB versus CMYK, cyan, yellow, magenta, and black. K is the black color plane. RGB, that's typically not going to have a white color plane because when you combine red, green, and blue, you get white. When you combine cyan, yellow, and magenta, you get black. Here's the key. You start out with a white background and you add inks and they absorb, right? Because this is what it's saying over in here. When you have a photon, its life cycle is to be absorbed. So light is coming in passively from the ambient area, right? It gets absorbed by the page. So the inks that look green are absorbing all light except for green, which then gets reflected. So this is a subtractive color synthesis system. You add cyan, yellow, magenta, and black, cyan, yellow, and magenta in equal amounts, and it will look black. The only reason they have a black color plane is because they do what's called gray component removal. They remove equal amounts of cyan, yellow, and magenta into the black plane in order to reduce the amount of more expensive inks. Pigments in cyan, yellow, and magenta are more expensive, but also they're able to make a clear black text because they're not trying to overlay red, green, and blue. They can never align them exactly, because if they were to align them exactly, you wouldn't have offset rosettes. So this is a key reason. If you don't have black, you can't get clear, clean text. You have to have that, or else people will look at it and they'll say, "Oh, this looks out of focus." Nobody wants to see sort of blurry-looking text.
That happens a lot.
You will see it from time to time. I don't know if you don't know. I hope you don't see it in my book. I'm checking. Cyan, yellow, magenta, and black are important when you're using a subtractive color synthesis system. That is a color synthesis system which is taking light away by absorption. Whereas red, green, and blue is very good for an additive color synthesis system, which is to say it adds light to the background, and if you add equal amounts of red, green, and blue, it will appear black. When you look at the black squares in this slide, what you're seeing is the absence of light. When you look at the white background, you're seeing the combinations of red, green, and blue. So in the subtractive color synthesis system, we're painting with mud, and in the additive color synthesis system, we're painting with light.
So where would black be on that color spectrum?
The pure spectral light color spectrum.
With the
You could make black anywhere you like, because in this spectrum, all you have to do is stop emitting any energy. Right? In other words, if I turn off the lights in this room, it will appear black. It's a subtractive color, right? You take away all of the additive energies, and there's nothing left. You don't see anything.
So wait, if something's red, for example, and you turn off the light, then is it still red?
If you can't see it,
Is it still red?
you don't perceive it as red. You see it as black because it's, if I turn on a white light, you see a white light.
Yeah.
Now, if I turn off the white light, is it still white?
No.
No, because it's off.
As in, like, say something like
No?
say if this wire was red, because you see colors.
Oh, I see. No. Here's an interesting experiment, right? If you have a here, I'll take this. Here, take a green object like the like this Puff's lotion tissue box that I'm holding. Illuminate it with a red light. Is it still going to look green? No, because it's only going to reflect the emissions that are impinging upon it. So it will look red. So if I shine a red light on this, nice strong red light, turn off the lights in the room, you're not going to see a green box. You're going to see a red box, because that's the only light that it can reflect. So the answer is the red is a sensation that your mind interprets from what your brain is stimulated by through your eyes.
So it's not real.
Red is just a color name. It's a perception. It's just a perception. If you want an objective measurement of color, right, what you want to do is you want to measure the wavelength emitted by this box under a controlled lighting circumstance. So you need to determine how you want to illuminate this box before you can proceed to give it an assigned color name. So you can give it what they call a controlled color temperature lighting assignment. And within that color box, you can then proceed to make a measurement. So when you take this color to the Home Depot and you say, I want a paint that looks like this, they will put it into a photodensitometer, which will emit different color lights and then measure what gets reflected off it, and then they'll determine what the pigments are for the paint that you want to add, and then they will match this color. So to do that kind of color matching requires a controlled measurement. I've actually tried this. You can go to the Home Depot with a piece of your wall and say, I want to do some touch-up. And they will take a piece of that wall, measure it with their photodensitometer, and they will mix up paint for you. And they'll say, here's that green, that ugly green you're trying to match. And by the way, why don't you just paint over the whole thing? And I'll say, well, because the boss won't let me, right? So, yes?
Oh, okay, so here's my question. We're surrounded by white light now, right?
Yes.
So
why are we seeing like different colors, like things that are different colors
Yeah.
differentiate?
Yeah, the material properties of different objects around us appear differently because they have material properties that are different. So if I said to you, well, how come the Dell mouse here looks like plastic? Well, the answer is because the material property of plastic looks substantially different than, let's say, the material property of the table you're sitting in front of, which kind of looks like wood. And so my claim is that this may have to do with the texture of the material. It may have to do with the pigments that the material was made out of. In general, if I look around, I can see a variety of different materials, right? I mean, this thing looks like plastic, and of course it is. This is a laser printer, but it's got multiple kinds of colors associated with it because the plastics have been mixed with pigments. And so those pigments are absorbing different colors. I see a green button in my laser printer, but that green is really a different green than this green. If I take this green and I say, look at that green, and I look at this and I say, hey, there's that green. Are these two greens the same green? They look pretty close, right? Your eye is able to differentiate one part in a million. So that's true, but your color memory, you only have 3 bits of color memory. This is why you have a Crayola crayon concept of color. You can know like 7 color names like me, and that's it. And when you close your eyes and I say red, you'll see red, but we'll see different reds. But if I take this color and I hold it up to that color, you'll see the two colors don't exactly match. And you'll say, aha, those are different colors. They don't have a smooth transition, because you can see one part in a million. That means you need to have at least 20 bits of color dynamic range in order to be able to see a smooth transition between one color and another. That's why people call 24-bit images direct color images, because you can smoothly change from one color to another without seeing a sudden change in the color. Similarly, if you want smooth glissando in sound with an oscillator, a digital oscillator, you want to have at least 20 bits of dynamic range as you go from one frequency to the other. Otherwise, you'll hear the steps as you go from one frequency to the next. So that sensation and perception is true not just for your visual system, it's also true for your audio system. That's interesting, isn't it? There is a thing that people do that stimulate both your eyes and your ears at the same time in video art. And when you start to see something, a third thing, right, that is an emergent property from stimulating both, they call it synesthesia. Synesthesia sounds like a made-up word, and perhaps it is, but in fact it's an accepted term in the field now. So when you are in computer graphics, we want to try and make different materials appear differently. What you do is you assign them a coefficient of specular reflection, a coefficient of diffusivity. And what they do when they have diffusivity, if they get illuminated, is they tend to diffuse the light around them and start to illuminate objects around them. So if I shine a light onto something that has poor diffusivity, such as this coffee mug, it doesn't really illuminate very much around it. But if this coffee mug had a high specular coefficient to it, if it was mirrored, then it would reflect the light efficiently and illuminate the stuff around it. Computer graphics programs give you tons and tons of material property parameters that you can assign to an object in order to make it appear realistic. They call it photorealistic rendering. And then there's a question of whether or not the simplifying assumptions that you might like to make I shouldn't say are good. How about are warranted? All right? So whenever you make a simplifying assumption, you always have to ask yourself a question, is the model based on that simplifying assumption good enough? Right? If you remove all fluorescence from your computer graphics, will you be able to model all the things you want to model? And if the answer is yes, then you can remove that. If you want to remove phosphorescence, I guess you could do that too. But here's an interesting point. If you take a Blu-ray laser and shine it on live human flesh, you can do what's called in vivo histopathology. You can have diseased tissue light up. It's called laser-induced autofluorescence, and what happens is one wavelength goes in, another wavelength comes out, usually a lower wavelength. And so you can use the high-frequency Blu-ray laser, and you can light up endometriosis, and it just comes back and it says, yes, hi, here I am, diseased tissue, which you otherwise wouldn't have seen. Now, a lot of times what people will want to do is excise the tissue, it's no longer live, and then do the analysis, and they call that histopathology. That's normal histopathology. But if you want to do the in vivo histopathology while you're inside the body, and you want to look around for diseased tissues like polyps or cancer or whatever, bruising, you can use interesting illumination systems, and they will come back with different wavelengths. So eliminating something like fluorescence may not be to your advantage. In fact, fluorescence may be a very important part of what you can achieve when you use different colors. And you don't have to use dyes to get those fluorescence. And the dyes can be nasty. What's isotropic? Yeah, it's a uniform reflectance. What's the opposite of isotropic? What's it called? Mesotropic. Mesotropic.
Did I make that up?
You did. It's a good thing. I like it. It's very creative. Good guess. The answer is anisotropic. But I like mesotropic. I'm not sure what it means. You could Google it and you could tell me. That's what you're doing? Yeah. Is that a word? Mesotropic? No? Well, it is now. What would you like it to mean? Well, mesotropic. Okay, that's close. What's mesotropic?
Having a moderate amount of dissolved nutrients.
Dissolved nutrients?
Yeah.
I don't know. It's who?
It's quality of the body of water. Having a moderate amount of dissolved nutrients.
Huh. I never heard that term. Learn something new every day. So there. Here's the color response curves in your eye. Let's see if I can identify. Oop, there we go. Here's blue. We're pretty you could sort of see, if you have a Blu-ray laser, it has to be much more powerful to have the same apparent brightness than, let's say, a nice green laser, because the green laser is really running at what appears in your eyes to be the maximum sensitivity. And then here comes the red laser. That's the A laser over in here. Actually, red would probably be closer to right about in there. Maybe it's in here. I'm not sure. 532 is green. This looks like 580. So now when we look at the RGB color cube, we also can look at the cyan, yellow, and magenta color cube, and we can see that cyan, yellow, and magenta are the dual of red, green, and blue in the color system. White is in the front over in here. Black is in the back. You can't really see it from here. And there's green opposite yellow. And you can get smooth color transitions between green and yellow if you have sufficient dynamic range in your color system. So here's an interesting point. RGB are orthogonal. They are embedded in a three-dimensional Cartesian coordinate plane. They allow us to span a three-dimensional space, and we can create an arbitrary vector in that 3D space. I can pick a point, an arbitrary point, in RGB 3D color space. And then I can pick another point in the RGB color space. And then I can smoothly transition between those 2 points. And as I do so, I create a locus of different colors. And I can smoothly transition from one color to another as I move from one point in RGB color space to another point. So when you think about white as a point in the RGB color space, and you think about black as another point in the RGB color space, we can devise color coordinates. If black is coordinate 0, 0, 0 at the origin of the three-dimensional Cartesian coordinate cube, and white is 1, 1, 1 at the as a unit vector on the main diagonal of the Cartesian coordinate cube, I can smoothly transition between the white point and the black point and create a locus of different gray points which go between the white and the black. Similarly, I can pick a point, let's say here, 1, 1, 0, which I'll call yellow, and green, 0, 1, 0, which is down in here in the lower left corner, and I can smoothly transition between those points in color space, which is exactly what you see when you look at the edge of this cube. So what we're really looking at is the locus of points that are spanning the space in the direction between green and yellow. Yes, sir?
Can you go past those points?
You sure can.
Like 2, 0, 0,
Yep, you can. The ability of your display to show that, for example, you'd say, well, what happens if I want a negative blue color? The answer is you can get that, you can model it, you can represent it, but when you want to display it on your screen, unfortunately your pixels can't be negative. So your screen doesn't afford you the ability to show it, at least not your computer screen. On the other hand, if you are in the NTSC color system and you're looking at color bars, there is a blue section which is bluer than blue, and it actually goes negative. But that's because they're using it as a calibration, and you rarely see that in computer graphics. You would see it in communication systems, but you don't see it in computer graphics. So the answer is yeah, you can have negative color, you can have colors that go beyond the bounds, but in fact the reason why we have a normalized device coordinate system for color that goes between 0 and 1 is because in general we're not exactly sure what our dynamic range will be for a pixel. Maybe there'll be 256 values for red, green, and blue, maybe more. But if I use numbers that are floating point and go between 0 and 1, I can represent any dynamic range I like, assuming I have enough dynamic range in the floating point numbers. And in general, they're always much higher in dynamic range than the fixed point image processing programs we're exposed to. It's quite normal for us to have a lot more dynamic range in something like a Hubble Space Telescope. Any scientific instrument will have more dynamic range than a simple computer graphic display. Hey, Brian. Welcome. You're a little late. Okay. You missed the midterm. Um, yeah, I'm going to describe the whole thing all over again, but I mean, dude. So, anyways, I beg your pardon? So what we were talking about here, before you walked in, was additive color synthesis systems. Here's red, green, and blue, and here you can see how red, green, and blue can be combined to create white, and how the absence of these colors allows us to create black. So I can create a gamut of colors. And so this vector space, as defined by the RGB cube, allows us to efficiently express all the possible colors that our computer can display. So as long as we're inside the cube, we can create colors that we can show. Moreover, if we're in the RGB color space and we want to print what's on the screen of our computer using a subtractive color system such as an inkjet printer or a what do they call these things? Color laser printer, or a thermal dye sublimation process printer, or some other exotic, wonderful hot wax printer, which is going to print our wonderful images onto our T-shirts. I've done that before. It's great fun. Yeah, it's an iron-on. You take a hot wax printer, you run a substrate through it. It's kind of plasticky wax paper. It deposits the wax onto the paper, and you take the paper and you iron it onto your shirt, and so then you have an iron-on computer graphic. I still have some of these at home. I don't wear them because it'll flake off eventually, and I don't want to wear them in part because I don't want to wash them. If I wash them, then for sure it'll be hard on it.
Are they like special?
Special? Well, they're special to me.
Oh, what are they?
Pictures. They're pictures of HDTV image sequences I made for the FCC while I was at Bell Labs.
Oh.
Yeah, this is before HDTV, back in the 90s. Back in '91, and they didn't have HDTV. They had proponents of different standards. The HDTV standards were being battled out by industry. The big shots in industry were AT&T Zenith, MIT, and RCA General Instruments, and they had different standards that they wanted the FCC to adopt. During the battle for the standards, people like me were running up against people who were perhaps working for Philips North America, and we had to create test sequences that broke the opponent's standards and made our standard look great. And so I would take my image sequences and I would turn them into T-shirts and wear them around the house. Geekware. So the RGB color space that runs between 0 and 1 gives us a kind of device dependency once we know something about the device itself. But until that time, we can use our device-independent color space, our coordinate system, which ranges between 0 and 1. And then we could translate it using different transfer functions. So if we know something about we'll call it the gamma or gain that we might get from our display, then we can translate from the color space, I'll call it normalized device coordinates in the color space, into the device-specific coordinates. So we can calibrate our display so that the colors look right. So this color space that people decided to use to give you device-independent colors was called the Commission Internationale Éclairage, or d'éclairage. I can't pronounce it properly because my French sucks. They gave us an international model for a device-independent color space in 1931. And there was a nice way to go and create all the different colors in the CIE model. So this gives us a mechanism for measuring what's called chromaticity. Chromaticity is very similar to what I would call the NTSC model for color. NTSC is the National Television Subcommittee standard for creating color television back in 1954. And they used a model which was called in-phase, luminance, and quadrature. Luminance, that's the overall brightness, and you can see that here in the Z component. And in-phase and quadrature would be the X and Y. So you can use any three orthogonal coordinates to represent arbitrary colors. They don't have to be RGB. You can just call them X, Y, Z. And then you can translate to any different coordinate system using what's called in linear algebra a change of basis. So anything that spans the color space can be used as long as the basis gives you the ability to reach all the points in that space. So here's the color space basis in X and Y, and then to change actual intensity you come out of the plane. That's Z. So now with this X and Y color space, you can proceed to use what's known as calibrated color temperature in order to be able to describe the different colors. Color temperature is an interesting idea. And what you do is you take a piece of carbon and hollow it out so that it has a cavity. Then you take the carbon and you raise it in temperature. Eventually, when it gets to a certain temperature, it will start to glow red hot. If you keep going, it gets hotter and hotter and hotter. At about 5,000 degrees Kelvin, it'll look like it's white hot. And that is what they call a daylight calibration standard. And the way in which you can get the color temperature is a function not just of the temperature, but it's also a function of Boltzmann's constant. So what people do is, and this is something you could do in a physics lab, is you can get a calibrated color for a given temperature. But when you go to the Home Depot and you want to buy a daylight color fluorescent bulb, they'll describe it as being a 5,000 degree Kelvin bulb. So effectively, it gives you the same white light that you would get if you took a piece of carbon and raised it to 5,000 degrees Kelvin. So they use these things as calibrated color sources, and then they proceed to devise mechanisms whereby they can sell commercial products that give you lights of those calibrated color temperatures. I don't know if you've ever noticed this when you go shopping for fluorescent bulbs, but it's one of those things. They give you color temperature. So that color temperature is something that the CIE attempts to directly address. And in fact, one of the CIE diagrams given here is showing you the colors that can be spanned by an RGB color system. The RGB color corners are right in here, but the overall colors that you can see go beyond what it is your computer display can show. And sometimes I think people like to alter what the colors are that you can display in their span by giving you a little bit of a variation. I think Sharp had an interesting display at one point which was supposed to give you more vibrant colors. And there was this guy, Mr. Sulu, George Takai, I think his name is, the guy who was he was the navigator for the old Enterprise shows from the 60s. He used to be the voice of the Sharp display. I think they dressed him in a white lab coat, and he looked like a scientist, although everybody knew he was just an actor. So here comes the black body radiation diagram, which is in the center of the CIE diagram, and these numbers are degrees Kelvin. And this is a color temperature of 6500 degree Kelvin, and this one here, which is called equal energy, is a daylight bulb at about 5000 degree Kelvin. So now you can kind of see what the different color temperatures look like with black body radiators. That's kind of cool, actually, right? So when we try to obtain the measurement from the power spectral density, what we're really doing is we're taking the color, C, at a given wavelength, and we're correlating it with the X, Y, and Z basis components in the CIE diagram. And that gives us an actual color coordinate in X, Y, and Z. So when we're looking at CIE chromaticity coordinates, we're looking at normalized device coordinates. And those normalized device coordinates are generally able to give us arbitrary colors in this gamut, and then we have to take those normalized device coordinates and translate them into the display of choice. Could be a printout, an arbitrary color system. There's a substantial overhead, I would say, in working in chromaticity coordinates. And that overhead comes about because you're dealing with floating point numbers. Remember that this is something that you need to do for each pixel. And if you start to do floating point computations for every pixel, it can be cumbersome. On the other hand, if you look at the DICOM images, biomedical images are quite capable of working with floating point numbers. That is one of the kinds of images you can deal with. We never used to have this problem until we started to work in real scientific imaging. And then once you get into the real biomedical imaging, you start to see these kinds of things happening, where you get 16 bits per pixel or 32 bits per pixel or floating point numbers for each pixel. Here's a image of what's supposed to look like a 25,000 degree color temperature. It's glowing blue. It's a, how do I call it, blue hot? So hot it's turned blue. So it's gone 2,000 degrees, it's red hot. It looks to me like at 5,000 degrees that's supposed to be white. At 9,600 degrees it's almost bluish white, and at 25,000 degrees it's so hot it's blue. Although, I don't know why you would say that, because blue normally corresponds to something that you would think of as cold. But there it is. The blue flame is hotter than the other thing, but if you have an infrared color camera and you're showing sort of like the windows, the parts that are supposed to be cold you represent as blue, and the parts that are hot you represent as red. Right? But like you said, if the flame is glowing blue, then you say it must be the hottest part of the flame. So I'm with you on that too. I guess it's arbitrary. So I've got CMYK for printers, RGB for displays, in-phase luminance and quadrature for television. Y is luminance. Don't ask me why. That's the way they did it. I can convert from RGB to IYQ using a 3x3 matrix multiplication. So if I take a 3x1 and multiply it by, I'm sorry, is it 1x3? Take a 1x3 and multiply it by a 3x3, I'll get a 1x3 on output. Yeah.
What's IYQ?
IYQ is in phase, quadrature, and luminance. And then HSV stands for hue, saturation, and value. So when you go to your television set, I don't know if they have this anymore. Actually, it might be in the menu for the on-screen display. But I remember when color televisions were analog, okay, and they had a tint control, and that was changing the hue. And they also had a brightness control, and that was changing the value. And then they had a saturation control, and that would change the intensity of the color. So you could, with saturation, you could make the red practically fluoresce by cranking the saturation all the way up. I'm not sure exactly if you can do that with a modern HD TV in the on-screen display menu. I haven't really mucked about with it sufficiently to know. I'd probably end up ruining it by the time I was done. So I can convert from RGB to HSV with another 3x3 matrix multiplication. In fact, I can go from any coordinate system, any three, I can do any change of basis with a 3x3 matrix multiplication, assuming I'm dealing with a 3-space basis vector. So why do we care about hue, saturation, and value? And the answer is because it's fairly close to how our perceptual system works. But when you're in the hue, saturation, value space, it doesn't necessarily look like a square color cube. It looks more like a cone. And when you change the hue, you're rotating around in the cone. And when you change the saturation, you're changing the magnitude of the hue vector. When you change the value, you traverse up and down in the cone. For me to go to the cyan, yellow, magenta space, because it's a subtractive color synthesis system, all I need to do in the normalized color coordinates of red, green, and blue is subtract from 1. So if R, G, and B are ranging from 0 to 1, to go to cyan, yellow, and magenta, all I have to do is subtract from 1, and blammo, I'm in cyan, yellow, magenta space. If I want to add a black ink color plane to cyan, yellow, and magenta to make it CMYK, then I take equal parts of cyan, yellow, and magenta and remove them to the black color plane, and that is called gray component removal, or GCR. Yes, sir?
I know you previously went over the two color spaces, right? RGB and cyan, magenta, yellow.
All before you came here.
Well, that was like earlier. And so printing is done with cyan, magenta, and yellow, right?
Right.
You kind of went over why that is, but why hasn't it progressed into the other color space? Why can't it be done, or is it possible to use red, blue, green?
Yes, yes. You can print with red, green, and blue inks, but you won't get the same span of the color space if you print with cyan, yellow, and magenta inks, because cyan, yellow, and magenta will span the subtractive color space. Red, green, and blue will not. They won't span the space. So you'll get a color triangle, but it will have vertices which are inside of the color triangle of cyan, yellow, and magenta, and they won't give you a full range of different colors.
Okay, I think I see.
They won't span the space, as they say. So here's some sloppily added matrix multiplication, and I wish I could make that nicer. Isn't it? Why is it like this? Can I push it over to the side? There it is. So this is how you do it with a 3x3 times a 3x1 giving you a 3x1. This is how you do a change of coordinates. So now it's very clear that they are equivalent. It's also clear that the determinant of the matrix is not 0. It's also clear that means it has an inverse, which means I can find the inverse of the multiplied 3 by 3 and go from IYQ right back to RGB. Because how do you find the inverse of a matrix?
Yep.
What do you say?
But like actually.
Wolfram? Calculus?
Okay, yes, MATLAB is the answer. We don't know the question, but we know the answer, and it's MATLAB.
Teach us.
Okay, I'm going to take away your MATLAB now. Let's assume that you can only work with the computer that exists between your ears.
What kind of world is that?
Oh, jeez. Back in the days of Gauss, back before there were digital computers, people were able to find the inverse of a matrix.
Wait.
Yes,
There
it's.
are digital
Was there a time? Before electricity and flushing toilets and running water, we had mathematics. And in that time, people were able to do things. They had a straight edge, right? They had quadratic tools, and they were able to take the inverse of a matrix. Determinants, yes. How did they do that?
Take the first two and you put it outside and you just cross multiply minus the other way.
It's the transpose of the cofactors divided by the determinants.
That doesn't make sense though.
It's true. All right.
Can we do an example?
Don't they have this on Google? It's the transpose of the cofactors. Don't they have linear algebra where you're from? You guys went to... Don't they do this in high school? The transpose
And then I came to college and I learned what MATLAB was.
of the cofactor divided by the determinants. Determinant is the inverse of a square matrix. There it is. The adjoint matrix is the transpose of the cofactor. Yes, the adjoint. I knew that had a name. All I could think of was transpose of the cofactor, but in fact, if I said adjoint, that would have made it no more clear for you than if I said transpose of the cofactor. So that doesn't help you at all. So you wanted an example. Here's an example. Straight off the web. I Googled it. So let's see now. How does this work? Oh, you take the 1, and then you get the submatrix 1, 1, 2, 3. Then you take the 2, and you get the submatrix minus 1, 1, 1, 3. That's over here. Then you take the other submatrix with 0, and it's minus 1, 1, 1, 2. That's over here. You form the determinants of these things by cross-multiplying. Then you subtract with the cross-multiplication. Then you add with the cross-multiplication. Then you go through and you make the next submatrix, and this is called the cofactor matrix. Then you take the transpose of the cofactors. That means you take that and you move it there, and you take this, you move it there, and you take this, you move it there. So you flop it around, and then that's about the main diagonal. The main diagonal doesn't change. And then you divide through by the determinant. There's 9, and blammo, you've got the inverse of A. And that's it. And when you take the inverse of A and multiply it by A, you get the identity matrix. And that's how that works. And that's how you do that. How's that for a quick example? I Googled it.
That's cool. The identity matrix, is it always going to look like that, or is that just in this given case?
The identity matrix for a general answer is always going to have 1s on the main diagonal. Yes. So when the row index equals the column index, you're on the main diagonal. So at 1, 1, 2, 2, 3, 3, 4, 4, all those values will be 1. And that will always be how you express the identity index, the identity matrix. Moreover, in math, we assume matrix indices start at 1. But in C or C++ or Java or C#, we assume matrix indices start at 0. So this is a discrepancy between the programmer and the mathematician, I guess. So if you wanted to, you could say it's index 00112233 instead of 112233, like that. So this is how you do it for a... and if you're in Java and you want to find the inverse of a 3 by 3 matrix, you can find it in the MAT2 class. I have efficiently, or MAT2 will be a 2 by 2. MAT3, I should be able to get the inverse. I hope I got the inverse. Invert. There we go. And so what I did here is I used Maple to synthesize a, this is the Maple code right over in here, which gives you an optimized way to do the exact same thing that we just talked about, the transpose of the cofactors divided by the determinant. So there's the determinant right down in here. You can kind of see it. And then there's the transpose of the cofactors, creating a new matrix. I got it for a 2 by 2 as well. This will do it in, how do I call it? CPU minimized time. You're trading a little space for time by creating the auxiliary variables. So there. We learned a little linear algebra, whether you like it or not. Actually, it's not a bad thing to know. It's especially nice to see it refreshed because you probably saw it all before, but then forgot it because you never used it. But now you have an application that you never thought of before, and they wouldn't have told you about before, right? Because in high school, they don't teach you about these things. They don't say, oh, and you need to know about matrix multiplication because of color. They never say that. Wouldn't that be nice? And you could say, but Professor, is this useless? Such questions are considered rude. Back of the class. And the answer, of course, is, I have no idea. I guess it's useless. I can't think of anything to do with it. But in fact, if they had an application for it like this, they could say, yes, you can't watch television without it. Ah, that's useful. So here is the color space in the HSV representation, and now what's I think very interesting here is we're no longer in the land of the square, right? This is no longer cube land. We're now in the land of the color cone. And in the color cone, as we change hue, we're actually rotating around a circle. And when we change value, we traverse up the cone, so that's increasing luminance. And when we want to change saturation, we're increasing the magnitude of the vector in the hue space. So when you're in an analog color television set and you are whacking on the hue dial or tint, what you're really doing is you're rotating the color vector. And if you look at the analog display of a vector scope inside of a studio, you will see it rotating. You will see the color vector rotating around the axis called the value axis, which is kind of cool. I don't know if you guys have ever seen a vector scope. They've gotten quite passé because people have gone HDTV and everything's digital. But vector scopes are just like O-scopes with a difference. I don't know if they have a picture of a vector scope or even a vector scope. Vector scope. Yep, there it is. That's a vector scope. And this is showing now, this is very typical vector scope display. Let's view the image. So now you can see, here's the red, green, and blue basis vectors. Here is the cyan yellow, and magenta basis vectors. This is the minus I, there it is, minus I signal. The Q, that's the quadrature. And there's the luminance, L. And this is exactly what you would see if on the display were a standard SMPTE color bar test pattern, which would look like this. Let's see if I can get this properly shown. View image. There it is. So then, this is kind of cool because it directly answers Kevin's question, can you have a negative color? And the answer is yes, you can. In the NTSC system, you can have something that is bluer than blue. It goes outside of the color space, and it's what they call the minus I test. So to make minus I, they use a bluer than blue signal, and it can be represented in the vector scope, even if it isn't represented in the display. So that's kind of cool.
I have a question.
Yeah.
If it's bluer than blue, then it's just blue in the display.
It's just blue in the display. It's bluer than blue because it allows us to create a voltage excursion which goes below the zero threshold of the pedestal inside of the NTSC signal. So the NTSC signal has what they call a front porch and a back porch. It has a sync pulse, which goes quite negative. It has what they call a subcarrier burst, which is 11 cycles of 3.58 megahertz, and then that's used by a gate to lock on to a phase lock loop with a difference. And the difference is it has a sample and hold. So what it has is a voltage-controlled oscillator, or VCO, which attempts to reproduce the exact phase of that 3.58 signal so that it can do what's known as a color reconstruction. So it's a very clever system because they retrofitted a black and white color system with color, a black and white non-color system with color, and that was done in 1954. They didn't want to change all the sets, so they wanted to add color to the signal. So to do it, they had to encode not just luminance, but the in-phase and the quadrature. And so in order to be able to reconstruct that with correct phase, they had to provide an accurate, synchronized oscillator. And to synchronize to that oscillator, they have to reproduce it in every line of the NTSC transmission. And so they give you a small color burst, that 11-cycle burst, and they lock onto it in order to be able to do a reconstruction. Cool, right?
Well, yeah, that's good enough for me.
Yeah. So it's more about television than you ever wanted to know. They should actually have something that shows you what an NTSC color burst looks like. I'll call it subcarrier burst. They should have like an image of this. Color burst, images. They show the color burst right in here. There it is, view the image. So there's the color burst. So that's 11 cycles of color burst right in there. And then here's your negative going sync pulse. And so you need to lock onto that with your phase lock loop, and then that will proceed to regenerate the color burst during the entire time that the signal is transmitted. That color burst is then used with a ring modulator, which basically takes, it's like what you call a double sideband modulation system. It takes one carrier, the subcarrier, and it multiplies by the incoming signal, and it gives you two sidebands, the carrier plus the frequency and the carrier minus the frequency. That's called double sideband modulation. And so what it does for reconstruction for color is it uses both of those sidebands when it goes to decode the color. And that's how that works. Cool, right? So, in fact, for the longest time, the analog standard definition television transmission signal was the most complicated signal in the home till people had like computers or something. So now we know something about color television. That was interesting, right? We know something about HSV, the HSV system, which we can arrive at using a simple 3x3 matrix multiplication. Here comes our RGB color space, colored nicely so you can see what the basis vectors look like. That's supposed to be 3D, by the way. I don't know if you can kind of see it. Close your eyes, you can see it. No, if you close your eyes, you can't see anything. So here we are constructing cyan, yellow, and magenta. The yellow doesn't show up too well. Who knows French well enough to pronounce this? Commission Internationale de l'Éclairage. Somebody say this properly? I know I'm butchering it, okay? And so if you have this, I'll call it normalized color coordinate system, you can get all these wonderful chromaticity diagrams, and then with them you can represent arbitrary colors within the human visual system. But representing the colors is very different than displaying them. The only colors that you can actually display are the ones that are inside this triangle. But if you want to go bluer than blue in the NTSC system, you're probably down in here somewheres. And when you're in the cyan, magenta, yellow system, right, you're in subtractive synthesis land. When you add the colors together, it gets black instead of white. And the reason why is because we're dealing with the subtractive colors. The absorption of light requires that we absorb everything but the light that we perceive. So a green pigment must absorb everything but green. It reflects green. And so I like to say we're painting with mud instead of painting with light when we're using a cyan, yellow, magenta, black color system. And here's how you do the translation from one system into the other. If you want to create gray component removal for equal parts of red, green, and blue, or cyan, yellow, magenta, in order to create a black color plane, you use something called the Nijberger equations. Fancy name for a simple idea. You know they're academics when they have fancy names for simple ideas. So how do you match color? So I go to the Home Depot, right, and I say, mix me up this paint. I want to do some spot painting. Is it break time? Oh, yeah, it must be break time.